Hi everyone, this is a presentation that goes along with a new paper entitled Accountable Liveness. So my name is Tim Roughgarden, and my great co-authors on this paper are Andrew Lewis-Pye, who's at the London School of Economics, Joachim, who's my colleague at A16Z Crypto, and Luca Zanolini, who's at the Ethereum Foundation. And before I get started, right, so, while I am both at Columbia University and the head of research at A16Z Crypto, this is a purely academic talk. Needless to say, nothing I say in this presentation should be construed as legal or financial advice. So this paper is about really a quite basic question, which is if something goes wrong with a blockchain protocol, who is to blame? Now, blockchain protocols can go wrong in a couple different ways. Sort of one of the earliest attacks or failures that people worried about all the way back since the Bitcoin white paper is double spend attacks. So this would be caused by a consistency violation where a blockchain protocol reports some transaction as finalized and then maybe something happens in the real world as a consequence, like physical goods get exchanged. But then later that transaction is rolled back. It's kind of like, just kidding, actually that transaction is not finalized like I told you it was earlier. So that's a consistency violation, and that's a prerequisite for a double spend attack. And at this point, we have a pretty good understanding of how to sort of blame perpetrators of double spend attacks. Now, whether or not you can do this depends a bit on the consensus protocol that you're using, but in a wide class of consensus protocols, ones derived from so-called PBFT, so like Tendermint would be an example, Hot Stuff would be another example if you've heard of those protocols. In protocols of this type, the smoking gun of perpetrators of a double spend attack are going to be validators, so physical machines running the blockchain protocol, validators that provably deviated from the protocol by voting more than once, so voting for inconsistent blocks. Any validator which is correctly and competently following the code of one of these protocols will never vote for conflicting blocks. So if you see evidence of some validator doing that, you know they have deviated from the protocol. They are the ones responsible for a double spend attack. And this is the reason why in, for example, Ethereum, if a validator is caught in this way of voting for inconsistent blocks, then that validator, who's going to have some native currency locked up in a staking contract, they will have some of that stake confiscated. They will be slashed as punishment for their deviating from the protocol in this detectable way. Now, double spend attacks are not the only way in which blockchain protocols can fail. Like sometimes you see in the news that a blockchain protocol might stall, meaning for some period of time it fails to finalize any new transactions. So that's an example of a liveness violation. And the same question comes up, right? In the event of one of these stalls, one of these liveness violations, who is to blame? So again, using Ethereum as an example, there's a heuristic in the Ethereum protocol known as inactivity leaks, where if the protocol fails to make progress, fails to generate checkpoints for the blocks that are being created, then in fact, gradually validators who appear to not be participating will again have their stake gradually slashed. Okay, so that's sort of the idea of the inactivity leaks in Ethereum. That's their attempt to try to hold responsible validators that appear to be responsible for a failure of liveness. And the goal of this work is to provide for the first time sort of the foundations for how to think about liveness violations, how to think about accountable liveness. Who is responsible for a blockchain protocol stalling? And as we'll see in this work, the answer is quite a bit trickier, quite a bit more subtle than it is for consistency violations. So we are going to be studying this question in what's really now a fairly standard model of blockchain consensus. Right, so the consensus layer of your favorite blockchain protocol, fundamentally what is it doing? It is acting as a sequencer. Okay, lots of different users are submitting transactions to the blockchain protocol, which they would like executed in that blockchain protocol's virtual machine. They're coming in from all over the place. And the point of the consensus layer of a blockchain protocol is to coordinate all of the physical machines, all of the validators running the protocol, so that they act collectively, logically, like a single machine, so that they all process these transactions in some common order. Like at the bottom of this slide, transaction 2 followed by 3 followed by 1 followed by 4. So a little bit more formally, the name of this problem in the distributed computing literature is sometimes it's called atomic broadcast, sometimes it's called total order broadcast. If you're familiar with state machine replication, that's also a sort of very similar problem. This is the core consensus problem that really any blockchain protocol must solve. So again, transactions are coming in from all over the place. Just think of them as coming in from an environment. They're arriving at validators. Validators initially know perhaps about different transactions, and they need to come to an agreement on the sequence in which those transactions should be processed. So each validator maintains locally an append-only list of the transactions that that validator views as finalized. I might also call this a log or a history. And then again, the goal in consensus is to make sure all of these physical machines, like the 25 machines you see inside the cloud on the slide, they should all maintain exactly the same list of finalized transactions. Even though there's 25 machines, it should be logically as if it was a single machine. Okay? And if nothing else, the two properties you want of any consensus protocol is on the one hand consistency. So this is what rules out double spend attacks, for example. So once a transaction is viewed as finalized, it's always viewed as finalized, and all validators agree on the sequence of finalized transactions. And then of course you want liveness, which is as long as transactions are being submitted to the protocol, those transactions should in fact be processed, ideally reasonably promptly. And what makes this non-trivial is that in the real world, things can go wrong, right? Validators can crash, validators can get hacked by bad actors, the communication network might be having a bad day, either because of an attack or because, who knows, BGP routing is weird today. And obviously you'd like consensus protocols that are robust to all of these possible things that can go wrong. So you want a consensus protocol satisfying consistency and liveness. These properties are so crucial for what I'm going to talk about today. Let me just give a few more details. I mean, even if this is, perhaps review for you. So again, consistency, each validator maintaining its own list of the sequence of transactions it views as finalized. In a blockchain protocol, often those finalized transactions come in batches known as blocks. And for consistency, right, we do allow some validators to be maybe slightly behind others. Like here you see validator number 2, it still has to catch up to validator number 1 once it hears about the block B3 of transactions, but they're never allowed to disagree. Okay, so the two lists of transactions at different validators, they should never disagree on the relative order of any pair of transactions. Okay, so that's consistency. No disagreements on the sequence of finalized transactions allowed ever. And again, liveness just says if a transaction is submitted to the blockchain network, then at some point that transaction should in fact appear in all of the validators' local sequences. So in this work, we're going to focus on consensus protocols that work well, in fact, that have optimal resilience in what is known as the partially synchronous model. And all of the PBFT style protocols you might have heard about, including like Tendermint, Hot Stuff, etc., they are all examples of protocols that have this property of being optimally resilient in partial synchrony. So that will be our starting point, and then we're going to be sort of seeking protocols that, in addition to those baseline properties, have additional functionality relating to catching perpetrators of liveness violations. So perhaps you're familiar with these concepts. I mean, these are sort of old concepts dating back to the 1980s, but again, this is very sort of central to this talk. So just for completeness, let me talk through what do I mean by partial synchrony, what do I mean by optimal resilience in partial synchrony. So the partially synchronous setting, that's a model of a kind of semi-reliable communication network. It interpolates, it's kind of a sweet spot between, on the one hand, kind of like the very easy model of a synchronous network, where all messages get delivered promptly within some known delta amount of time. Delta is maybe like 2 seconds, something like that. So it's a sweet spot between that too easy synchronous model and the, in some sense, like too difficult asynchronous model, where literally message delays can be crazy forever, except that eventually, you just know that eventually messages are going to wind up getting delivered. So partial synchrony, the idea is you can have periods of asynchrony. So for example, representing a denial of service attack, or for some reason a network partition, but those sort of periods of unreliability are going to be bounded. And you would like very quick recovery to normal operations as soon as the communication network recovers and operates normally, i.e. consistent with the synchronous setting. So specifically, kind of the minimal version of this model is you just have 2 phases, an asynchronous phase followed by a synchronous phase. So there's some adversarially chosen global stabilization time called GST. That's the length of the period of asynchrony. And so things can be going crazy for a while, but at some point at GST, all of a sudden the network becomes synchronous forevermore after that. So following GST, messages are guaranteed to be delivered within delta time, within, say, 2 seconds. And the parameter delta here is known to the protocol, right? So you know how fast messages get delivered when the internet's having a good day, and then you don't know how long this attack is going to be. So the protocol is responsible for functioning properly, meaning having consistency and liveness, no matter what GST happens to be. So what can be achieved in the partially synchronous setting, where there's the magic threshold here of a third of the validators being compromised. So as long as less than a third of the validators are compromised, like they haven't crashed, they haven't been hacked, they're correctly executing the protocol as intended, as long as more than 2/3 of the validators are correct, then in fact you are guaranteed consistency always, even when the network's going crazy, even before GST. Okay, so you literally never have a consistency violation as long as less than a third of the validators have been compromised. Now, in general, during that period of asynchrony, when messages are not being delivered, you may lose liveness, you may stall for that period. But again, as long as less than a third of the validators have been compromised, you will return to normal operations once the network itself is normal. That is, after the global stabilization time, you will again start finalizing transactions, and indeed fairly quickly. So really proportional to the network speed, capital delta. You can also trade off liveness and consistency resilience in various ways. I'm showing you the symmetric case. I'm here for simplicity, and I'll stick with the symmetric case throughout this talk. But the results in this paper are relevant for all optimal trade-offs between consistency and liveness you might want to do, and the paper has details about that. So in this work, we will be taking as a hard constraint that our consensus protocols should satisfy these optimal resilience guarantees in partial synchrony. Those are our baseline requirements. And then what we're going to pursue is additional functionality above and beyond these baseline requirements. So the type of additional guarantees that we're going to pursue is some kind of non-trivial functionality, even in the bad scenario of a large attacker. That is, where at least a third of the validators are Byzantine, are deviating from the protocol. Now, to say anything in that case, we need to be ready to perhaps make additional assumptions, for example, timing assumptions on message delays, but just to be like super concrete, and ultimately our results will be more general than this, but to be super concrete, you could imagine saying, like, here's a protocol that, on the one hand, if less than a third of the validators are compromised, is guaranteed consistent and live in partial synchrony. And on the other hand, if actually more than a third of the validators have been compromised, and it happens to be a synchronous execution, then ... extra guarantees. In our case, guarantees about holding responsible perpetrators of a liveness violation. Next, I want to talk about accountable safety. And this is the work I was referring to in the very first line of the very first slide of this talk. If a blockchain protocol suffers a double spend, and therefore by necessity suffered a consistency violation or a safety violation, how do you identify some of the perpetrators of that double spend attack? So accountable safety answers that question. The theory of accountable safety, in my opinion, has been extremely successful. It's actually mostly just from the last 5 years or so. It feels like it could have been done in the 20th century because I think it's quite fundamental. But in any case, it's been very successful, and it's the natural model on which, ideally, we would like to base our theory of accountable liveness. So informally, a protocol satisfies accountable safety if whenever it suffers a consistency violation, there is a smoking gun, a certificate of guilt that implicates some of the responsible Byzantine nodes. Now remember, we're thinking about optimally resilient consensus protocols, so if there's less than a third compromised validators, you're not going to have consistency violations at all, and there's nothing to do. So accountable safety becomes interesting once the adversary, if you like, is large enough to cause a consistency violation, once at least a third of the validators are compromised or Byzantine. A bit more precisely, accountable safety is defined via a blaming function. So imagine a protocol suffers a consistency violation. What does that mean? That means there's two validators, honest validators, that got tricked into believing different sequences of transactions. So the blaming function is going to take as input the transcripts of those two honest validators. By transcript, I just mean all of the messages that they ever received. It's going to take as input those two transcripts, and from it extract a large set of Byzantine validators. And no false positives are allowed. So we really want it to be the case that no honest validator will ever be incorrectly accused by the blaming function. So every validator that it points to really should be Byzantine, really should have provably deviated from the intended protocol. So that probably seems kind of abstract, but honestly, for like the protocols you might be familiar with, which just sort of proceed using quorums, so where validators assemble, like a supermajority of votes before proceeding through sort of stages en route to finalizing a block, really this blaming function is just going to say, hey, two validators, just compare notes. Look at your quorum certificates. Why did you get tricked into finalizing sort of different sequences of transactions? It's because you had quorum certificates where lots of validators voted in both, voted for inconsistent blocks. And so there's your smoking gun, right? So right there in their transcripts are in fact the votes signed by the same validator for different conflicting blocks. So in this work, we're not going to worry about what one might do once one identifies a bunch of Byzantine validators. There's been a lot of nice work over the past couple of years. For example, if you want to slash them in a proof of stake protocol, how do you do that with provable guarantees? Again, that's all sort of important, nice work. But in this talk, in this paper, we just want to focus on the more basic question of how do you even identify the perpetrators in the first place? I asserted earlier that I thought the theory of accountable safety has been very successful over the past 5 years. So let me back that up with 3 cool facts about accountable safety. Facts that we'd certainly be very pleased if there were analogs of these facts in some parallel theory of accountable liveness. So cool fact number 1 is that accountable safety is basically without loss of generality, at least in the setting that we're talking about, namely optimally resilient protocols in partial synchrony. You give me any protocol of that type, I will graft on some additional logic and give you back a protocol that, in addition to being optimally resilient in partial synchrony, also has accountable safety. Cool fact number 2, it does not matter how many of the validators are Byzantine, how many validators have been compromised. Even if you have 98 Byzantine validators and 2 honest validators, and those 2 honest validators disagree about the sequence of finalized transactions, from the transcripts of those 2 honest validators, you can in fact identify lots of Byzantine nodes. So no additional assumptions required on the number of Byzantine validators. Cool fact number 3 is not only do you identify some Byzantine validators after a consistency violation, you identify a lot of them. Specifically, at least n over 3 Byzantine validators, where n is the overall number of validators. And remember, this is the minimum number of deviating validators you need to cause a consistency violation in the first place. So if you think about it, this is the best you could hope for. Okay, you may not get every single Byzantine validator because some of them may be sort of pretending to be honest and there's no way you can catch them, but you will be catching n over 3, the minimum number required to cause a consistency violation in the first place. Very cool. Honestly, not much more we could have asked for the theory of accountable safety. Those are really sort of powerful guarantees. So the natural thing to do now is say, well, let's look at the other major way that a blockchain protocol can fail, by stalling, i.e. by suffering a liveness violation, and let's aspire to an equally powerful theory of accountable liveness. Now, the definition of accountable liveness, I think, is more or less what any of you would write down right now, given what I've told you about accountable safety. We're going to need to make a couple small tweaks, which I'll tell you about on this slide, but basically there's going to be no surprises with respect to the definition of accountable liveness. So specifically, right, we're now talking not about consistency violations, but liveness violations. But in the event that we have a liveness violation, we would again want a smoking gun that implicates some of the perpetrators, some of the Byzantine validators that deviated from the protocol to cause this liveness violation. And again, we're thinking about the regime where at least a third of the validators have been compromised, are Byzantine. Otherwise, the protocol is not going to suffer liveness violations anyways. So again, we're going to make this precise using a blaming function. One small difference. So with a consistency violation, that's defined in terms of a pair of honest validators. If a pair of honest validators disagree, then you take their 2 transcripts to produce the certificate of guilt, to produce the smoking gun. A liveness violation, by contrast, isn't kind of just a function of a pair of honest validators. It means that no honest validators have successfully confirmed some transaction. So the input to the blaming function is not going to be 2 transcripts. It's going to be the transcripts of all of the honest validators. But based on that set of transcripts, again, the output of the blaming function should be some hopefully large set of Byzantine validators. And again, we want no false positives. We want it to be that under no circumstances could this blaming function possibly incorrectly implicate an honest validator. And again, we're going to not worry about what you would do after you've identified Byzantine validators. If you want, you can use some of the nice techniques developed over the last couple of years to either slash in a proof of stake protocol or sort of have a recovery procedure in the permission setting. We're just going to focus on the more basic question of how do you even identify who you would want to slash, who you would want to remove from the validator set. One other tweak we're going to have to make to the definition. So a nice thing about consistency is that you sort of know whether it's been violated or not, right? Like at a given time t, either 2 honest validators have at some point disagreed about the sequence of transactions or they haven't. Liveness is different, right? You don't actually definitively know at time t whether you've had a liveness violation because any pending message might be finalized sort of sometime soon. You don't know yet. So the way to have accountable liveness is it's a simple fix, but we're going to insist on a particular bound, a latency bound. So how long it takes for a transaction to be finalized after it's submitted. So L is going to be our notion for that latency bound. As a running example through this talk, I'm going to use 2 hours. If you'd rather that be 2 minutes, that's fine, but as you'll see, you would need stronger timing assumptions to get accountable liveness with respect to 2 minutes than you would with respect to 2 hours. Okay, so that's our notion of liveness violation. A transaction is submitted and it has not been confirmed, it has not been finalized by any honest validator within capital L units of time. Having nailed down the definition of accountable liveness, the question is now when and how can we achieve it? And again, we'd love it if we had those exact same 3 cool facts that we have about accountable safety. We would love it to have accountable liveness basically without loss of generality, like you can just add it on to any existing optimally resilient partially synchronous protocol. We would love it if we didn't have to make any assumptions about the number of Byzantine validators, and we would love it if we could guarantee that in the event of a liveness violation, we in fact identify a large number of Byzantine validators. And so it turns out, the hard part of this work is not so much the definition. Again, I think the definition of accountable liveness is more or less what you'd expect, but it turns out understanding the achievability of this property is very subtle, and that's what this paper is really about. And in particular, to achieve accountable liveness, we will provably need to compromise on each of those 3 cool facts we had about accountable safety. To achieve accountable liveness, we will need to make additional timing assumptions beyond those that are made in the basic partially synchronous model. We will need to have some kind of cap on the number of Byzantine validators. And we will not be able to guarantee as many Byzantine validators being implicated as we were in the case of accountable safety. That said, ultimately we will be successful in the sense that we will identify additional timing assumptions, we'll identify a cap on the number of Byzantine validators, such that you can in fact have provable accountable liveness, so that you can in fact hold a number of Byzantine validators responsible for a liveness violation. So at this point in the talk, I'm actually kind of curious what you think. Like, are you surprised that, as I'm asserting, accountable liveness is fundamentally harder to achieve than accountable safety? Or is that kind of what you were expecting? And I think different people could have different intuitions about this. But now that we sort of know that that's true, let's do some Monday morning quarterbacking and sort of look back and say well, in hindsight, why should we maybe have expected accountable liveness to be more difficult to achieve than accountable safety? So first of all, at least if you think about kind of the protocols that we know and love, Tendermint, hot stuff, etc., the deviation that causes a consistency violation is the creation of messages that should not have ever been created, like a vote for a block that conflicts with a different block that validator already voted for. So it's really caused by the presence of unexpected messages And then those unexpected messages are sort of the natural ingredients to use in the certificate of guilt, the natural ingredient to use to prove accountability. Whereas, again, if you think about the protocols that we know and love, like, why is there going to be a liveness failure? It's because messages that should have been sent were not sent. Like, people didn't propose when they were supposed to, or they didn't vote when they were supposed to. So you have to be proving the absence of messages you were expecting rather than the presence of messages that you weren't expecting. All right, so what? What's the difference? Well, the point is, you can blame the network for the absence of messages. Remember, we're in the partially synchronous model. There'll be periods of asynchrony, periods of long message delays. So you can blame the network for the absence of messages. You cannot blame the network for the presence of unexpected messages. The network cannot forge signatures on behalf of some validator to frame it as deviating from a protocol, right? Whereas the network certainly can delay messages for a long time in a way that's indistinguishable from Byzantine validators not sending messages when they were supposed to. So that's actually a quite fundamental distinction. And the last point, which may only really become clear when we talk through the proof of our second impossibility result, is that it turns out Byzantine validators have the ability to frame honest validators for liveness violations in a way that they simply can't for consistency violations. So remember, at least for the types of protocols that we know and love, consistency violations are caused by double voting, a single validator signing votes for conflicting blocks. So that would mean for Byzantine validators to frame honest validators for a consistency violation, they would somehow have to make up conflicting votes cast by honest validators. But that would require forging signatures, which we assume the Byzantine validators cannot do. So Byzantine validators cannot frame honest validators for consistency violations, but one of our impossibility results will show the sense in which they can for liveness violations. So let's explain the first compromise we're going to need to make. So again, our first cool fact about accountable safety is that you can basically have it without loss of generality when you're talking about protocols that work in partial synchrony. And the first uncool fact that we're going to learn is that in fact, accountable liveness is impossible to achieve in partial synchrony. So we're going to see one kind of trivial argument for why this is true, and then on the next slide we'll see sort of a less trivial, sort of more general version of why this is true. The trivial reason why this is true is that when you're working in the partially synchronous setting like we are, liveness failures can be caused by the network without any assistance from any Byzantine validators. So if you have a liveness violation and there's no Byzantine validators, you can't have a blame function, right? There's nobody to blame other than, of course, the network. So in a little bit more detail, so fix the liveness parameter you're interested in. Again, I'm just using 2 hours as sort of a running example. And then like in partial synchrony, right, for all we know, the network is going to be asynchronous for more than 2 hours. No messages might get delayed for, let's say, 3 hours until global stabilization time. So literally every single validator hasn't heard from anybody else. So then something which I think is intuitively clear, it does require proof, but intuitively, if you're a validator and you haven't heard from anybody else, you can't start just like unilaterally confirming transactions. Because if you did, then, you know, other validators might be confirming their own transactions and you would have a consistency violation. So without hearing from anybody, all of the validators have to stall. They have to do nothing. So 2 hours go by, that's going to be a liveness violation. But again, there's no Byzantine validator, so there's literally nobody to blame, again, except for the network. So for our more general and less trivial version of this impossibility result, let's actually impose some extra timing restrictions on the execution, above and beyond just what would be true in partial synchrony. Specifically, I'm going to make an assumption which I'm going to call for now half-synchrony. I'm not going to define that formally on this slide. I will define it later in the talk. But roughly speaking, you should say, in addition to being synchronous after the global stabilization time, the network is also synchronous at least half the time prior to GST. And the one thing to know for this slide about this definition is that it does imply that messages will be delivered after some known finite amount of time. So the point being is that the argument on the previous slide, where you just delay messages past the liveness parameter, that argument is no longer valid in half-synchrony. So if we want an impossibility result, we're going to need to have some less trivial argument. And indeed, while on the last slide, the issue was that there literally were no Byzantine validators to blame for a liveness violation, here there definitely will be Byzantine validators to blame, and it's just that the protocol will not have enough information to figure out who the perpetrators are. what we're going to show is that as soon as there's enough Byzantine validators to cause a liveness violation, as soon as a third of the validators have been compromised, at that point the adversary is already large enough to elude any attempt to identify who the Byzantine validators are. So if you've seen some impossibility results sort of about consensus protocols and you see this threshold n/3, you know the very first step of the proof, which is that you separate the players, the validators, into 3 different groups. Let's just say for concreteness, it's a 40-40-20 split, like on the right part of this slide. The plan then is going to be to concoct a scenario where, because of the delayed messages, honest nodes have no choice but to stall. Because if they didn't stall, they would be at risk of creating a consistency violation. Given that the honest validators stall for a long time, that constitutes a liveness violation, and the validators are then responsible for coming up with a certificate of guilt for blaming Byzantine validators, but we're going to show that there's still ambiguity in which set those Byzantine validators lie. So specifically, refer to this figure on the right, and forget about half-synchrony for the moment. Suppose we're just in the normal partially synchronous model, where, of course, we are responsible for being consistent and eventually live. And imagine, all the validators are honest, but we are pre-GST, so it's an asynchronous period. So think of like a 2-hour interval, and imagine that during the first hour, the only messages that get delivered are between A and C, and for the second hour, the only messages that get delivered are between B and C. And otherwise, all messages are delayed during this 2-hour interval. The claim, then, is that in this scenario, the validators of A must stall. They cannot continue to finalize transactions. And the reason is that if the validators in A actually did just forge ahead and confirm transactions despite all of these message delays, there'd be a different scenario, indistinguishable from A's perspective, a different scenario, one in which the validators in C are Byzantine, that trick the validators of A into finalizing transactions that conflict with transactions finalized in a different group B of validators. That would be a consistency violation when only 20% of the validators are Byzantine. And so that's not going to be allowed. Remember, our baseline requirements are, in particular, consistency and partial synchrony, if up to arbitrarily close to a third of the validators being Byzantine. So because we can't allow safety violations with a 20% adversary, as a consequence, the validators in A under this delay pattern must stall. Now remember, to this point, we've just been working in normal partial synchrony, not in half synchrony, where the network is synchronous half the time before GST. On the other hand, this example did not have any Byzantine validators. All the validators were honest. So the reason it's not half synchronous, right, is because between A and B, the messages get delayed for this full 2 hours, rather than just 1 hour out of the 2, like the other 2 pairs of groups. But imagine now that the group B were actually Byzantine validators, right? So then the delays between A and B could just be a result of B acting Byzantine, whereas the delays for an hour between A and C and the other hour between B and C could be the fault of the network. That's consistent with half synchrony. So given that the validators of A stalled before, they're going to have to stall now as well, because it's an indistinguishable scenario in which the validators of B are Byzantine and we're actually in half synchrony. And by a similar line of reasoning, you can come up with a second scenario, indistinguishable from the perspective of the validators in C, a second scenario where it's the validators of B who are honest and the validators of A who are Byzantine. Again, creating a stall, creating a liveness violation. And so at this point, pity the poor validators in C. There's a liveness violation. They know they're responsible for sort of invoking a blame function and identifying some Byzantine validators. They know, unlike the previous slide, they know there's some Byzantine validators. They're either in A or they're in B. They have no idea which. So you can't blame anybody without some risk of blaming an honest validator. So that's the sense in which non-trivial accountable liveness is impossible, even in this half-synchronous setting, where pre-GST the network's synchronous half the time. There's no non-trivial accountable liveness in the sense that as soon as the adversary is big enough to cause a liveness violation, as soon as there's at least n/3 Byzantine validators, at that exact same moment, the adversary is large enough to escape any possible blame. So what does that mean for us? It means we have to compromise even further. If we're going to have accountable liveness, it's going to be for executions that satisfy something that's at least a little bit stronger than half synchrony. The revised goal, then, that we're going to pursue is, well, as always, having this hard constraint of consistency and liveness and partial synchrony, we're going to pursue the weakest possible requirements on message delays so that in any execution that happens to meet those timing requirements, we will achieve provable, accountable liveness. We just saw that half-synchrony, whatever that means, I still have to define it, but intuitively, half-synchrony is not a sufficient condition on an execution to have accountable liveness. What I want to do on this slide is build your intuition about how even stronger timing assumptions might help. So for now, we're just going to talk through the extreme case where we ask for accountable liveness in synchronous executions. As you'll see, our main positive result is quite a bit stronger than that, but to build your intuition about why this would help, let's first explore the case of just synchronous executions. Now, I sympathize if at this point of the talk, you're thinking to yourself, like, how am I actually supposed to interpret these accountable liveness guarantees that hold only under additional timing assumptions, like in the extreme case in this slide for synchronous executions? Because that's quite a bit different, actually, than what we got used to with accountable safety, where it really is a smoking gun, right? The messages really are typically going to be, here are two different votes signed by the same validator for conflicting blocks. There's kind of nothing really to argue about at that point, right? That's just like a deviation from the protocol, can't possibly be the network's fault. Whereas what we're achieving here for accountable liveness, as we've seen, by necessity, really, instead of a smoking gun, we will get this proof in effect, that either certain validators must have deviated from the intended protocol, or message delays must not have conformed to the requirements that we imposed. Like again, on this slide, the execution must not have, in fact, been synchronous. And the evidence will not allow you to differentiate which of those two is the case. So, how should I interpret this? I would interpret this that, for accountable liveness, it seems a bit dangerous to do programmatic slashing based on sort of the evidence that the solutions that we give are going to provide. Because again, there is this possibility that it was just the network was much more messed up than we thought it was going to be. But you can imagine passing this evidence to some out of protocol process, which then adjudicates which of the two scenarios seems to have been the case. Whether it was in fact Byzantine validators responsible, in which case maybe you want to remove them, maybe you want to slash them, etc. Or if it was, in hindsight, seems to have been the network's fault, in which case you may just want to do nothing and proceed. All right, so now that my conscience is clear about how to interpret these results, let's go back to building intuition about if you were only trying to get accountable liveness in synchronous executions, what might you do? And ideally, we don't want to sort of invent some radically new protocol. We want to take the tried and true protocols, modify them in the minimal ways possible so that, in fact, we get this guarantee, so that we get accountable liveness, at least for starters, in synchronous executions. So you can start from your favorite sort of protocol that's optimally resilient in partial synchrony. I'm going to start from Tendermint. If you'd rather start from Hot Stuff or Streamlit or whatever, that would be fine too. And I'm not here going to do a detailed review of how a protocol like Tendermint works. There's lots of sources out there if you want to learn more. I'm just going to give you kind of the high-level shape of what the protocol looks like so I can explain the intuition behind the modifications we need to make to it to get accountable liveness. So these next couple of slides, they're just literally copy-pasted from the blockchains course that I teach at Columbia. Again, just to give you the shape of how a protocol like Tendermint works. And Tendermint has a lot of different versions. This is one particular version of Tendermint. All of these protocols operate in what are called views. So a view is a single attempt to try to finalize a new block. It may or may not succeed. Either way, once the view ends, you move on to the next view. Each view has a leader. A leader is a single validator, and the leader is responsible for, among other things, assembling a block proposal in a view. And then the rest of the view is going to consist of the validators voting on whether they think it's a good idea to finalize a block or not. So in the version of Tendermint I've sort of depicted here, there's a number of rounds. So rounds involve communication between the validators. So in this version, the validators first begin by sort of telling the leader everything they know about to get the leader up to date. The leader then makes a block proposal, sends that out to all of the validators. The validators basically declare whether or not they think the block proposal they heard about is reasonable, whether it's sort of sufficiently recent as opposed to stale. And then validators compare notes to try to come to agreement on whether enough of them have seen enough acknowledgments of the appropriateness of the block proposal to go ahead and finalize the block. Okay, so you have views. Within a view, you have these rounds. Each round is sort of setting up friction, that making it sort of a gauntlet that validators have to get through in order to finalize a block at the end. Remember, Tendermint and other protocols like this, the one thing they can never screw up, they can never have a consistency violation, at least if you have less than a third Byzantine validators. So they're very cautious, they're very risk-averse. Protocols like Tendermint, everything has to go right through all of these sort of stages within a view for the view to conclude with validators finalizing a new block. You have to hear the block proposal on time, you got to hear enough votes, you got to hear those votes on time, etc. If everything goes right, you conclude with a new finalized block. Otherwise, you skip the view sort of nothing really happens, and you just move on to the next view with a new leader. So this next slide has the corresponding pseudocode. I don't want you to actually read the pseudocode. This is just to show you how kind of the cartoon picture on the previous slide does translate to code. Okay, so delta here, that's the parameter that you assume in the partially synchronous model. You assume that's a bound on message delays after GST. So if a network's operating normally, then you assume message delays happen in delta or fewer time steps. And you see how each of those rounds we saw on the cartoon in the previous slide translates to a small snippet of code of what a validator is supposed to do at a prescribed time within the view. Okay, if it's the leader, it's making a block proposal. Otherwise, it's voting, it's sending messages, and perhaps if everything goes right, at the very end, it might finalize the block that was proposed in that view. So using that version of Tendermint as a starting point, let me talk through some additional logic you could add to it that will, in fact, get you accountable safety, specifically in synchronous executions. I think it'll be clear as we talk through it, there's no way this additional logic is going to interfere with consistency, always, in general partial synchrony, nor will it interfere with eventual liveness following GST. It's going to purely be some sort of, extra bookkeeping and reporting on top of the usual stuff that validators do in Tendermint. So the basic idea really is quite simple. It's really just to have all validators broadcast their progress to everybody else as they proceed through this gauntlet trying to drive toward finalizing a new block. Now, of course, if you're in the middle of an asynchronous period, you can try to notify other validators about your progress, but the messages you send out might take a really long time to get delivered. But again, remember, we're thinking about at least specifically for synchronous executions. Let's see if we can get accountable liveness. Now, if we're in a synchronous execution, and I'm a validator and I sort of broadcast out my progress thus far, in that synchronous execution, I know that all the other honest validators are going to hear about my progress at most delta time steps later. So for example, let's zoom in one particular round within a view of Tendermint. So, suppose you're a validator, an honest validator, you're not the leader, right? So at some point you hopefully hear a block proposal from the leader. Maybe you like it and you vote for it. So the next thing you're supposed to do in Tendermint, imagine there's 100 validators overall. You're going to be waiting to hear votes from 67 distinct validators, all in support of the same block proposal. That's sometimes known as a stage 1 quorum certificate. In the normal version of Tendermint, if you do promptly hear 67 votes all for the same block proposal, what you're supposed to then do is cast a new second stage vote in favor of that already quite well supported block proposal. In the modified version of Tendermint we're going to do here, not only will you be casting that stage 2 vote in support of that block proposal, you will also broadcast out that quorum certificate. You're going to share the evidence, the reason for why you're casting a stage 2 vote, namely the 67 signatures supporting the block proposal. You're going to send those 67 signatures also to everybody else. Which means, if you happen to be in a synchronous execution, you know that delta time units later, all the other honest validators are going to have exactly the same evidence that you had. The exact same reason you cast a stage 2 vote, they, in a synchronous execution, will now also have that same evidence. In other words, if it's a synchronous execution, other validators have no excuse for not casting a stage 2 vote. If there's some other validator, they didn't cast a stage 2 vote, and again, if it's a synchronous execution, you will know if they didn't cast it, because if they had cast it, you would have heard about it reasonably quickly. If they didn't cast a stage 2 vote, even though you knew they had the evidence to do it, that is then a guarantee that that validator is deliberately deviating from the protocol. They are withholding votes that by rights they should be casting. So that is the basic idea. You take each round from within a view of Tendermint, you make it a little bit longer so that in any synchronous execution, all the honest validators will hear about each other's progress, plus the evidence for that progress as they go along. And again, if you observe some validator not doing what it's supposed to be doing, again, thinking about a synchronous execution, where if they actually had sent the messages, you would have heard about it. So if you observe them not sending messages that they should have, then we're going to say, and this is a basic primitive here, we will say that validator I blames validator J. If I observes J not sending messages that it should have sent, given the evidence that I knows that J has, again, in a synchronous execution. So this is a basic notion for us. Within a view, one validator I blaming another validator J on the basis that it did not hear messages from J that it would have expected to hear from J in a synchronous execution were J honest. So this basic blaming primitive, this is the seed from which all of our accountable liveness guarantees are going to grow. So for example, imagine you have a liveness violation in Tendermint. That means you've got a bunch of views that failed to finalize a block. Okay, so zoom in on one of those views where sort of nothing happened. What are the possible explanations for why in a view of Tendermint you don't actually finalize a block? Well, there's actually several. The two usual ones that one thinks about is, first of all, it might be asynchrony, right? So maybe like the leader proposed a block in good faith, but just the network was sort of really bad, so nobody heard about it, so nobody voted, so nothing happened. Fine. The network is one reason why a view might fail to finalize something. But remember, we're now thinking specifically about a synchronous execution. So that's not a problem. Or we're assuming that's not a problem. So the second usual reason why you might not finalize something is you have a Byzantine leader. Okay? And a Byzantine leader in particular cannot make a block proposal. And if no one makes a block proposal, nothing happens in a view. So in the usual proof of liveness for Tendermint and other similar protocols, you say, well, suppose you're in a period of synchrony, like post-GST, and suppose the current leader is honest, which will certainly happen, periodically, then in that case, a view will successfully finalize a block. Now, here, we're in a slightly different scenario where the attacker is bigger than you're used to when you're thinking about Tendermint. Right? You prove liveness for Tendermint only when the attacker has less than a third of the validators, less than n/3 Byzantine validators. Here, the whole point is to think about adversaries that are big enough to cause liveness violations. So they're going to have more than a third or more of the validators. And so now there's a third reason why a view of Tendermint might fail to finalize a block, and it's because even though the leader was honest, even though the network's going great, it's a synchronous execution, the more than a third Byzantine validators withheld participation, okay, preventing the assembling, for example, of maybe a stage 1 or a stage 2 quorum certificate. That's the third thing that can go wrong when you have a big adversary. But the point is that if you do have an honest leader, and we'll see later sort of techniques for dealing with that, if you don't have an honest leader, if you do have an honest leader, and if you are in a synchronous execution, like we're thinking about, then you will actually successfully blame, say if there's 100 validators, you will blame 34 of the validators. They will be observed by honest validators as preventing making progress through the gauntlet. Let's move on to the second compromise that we're going to need to make for accountable liveness guarantees relative to accountable safety guarantees. Remember, the second cool fact about accountable safety is that you get it no matter how many of the validators are Byzantine. Even if you have 98 Byzantine validators and they cause 2 honest validators to become inconsistent, from the transcripts of those 2 honest validators, you will be able to identify a large number of Byzantine validators. That will not be the case for accountable liveness. We will need to cap the number of Byzantine validators. And it's really in the proof of this result that we see some of the intuitions that I mentioned earlier in the talk. We said, why in hindsight might accountable liveness be more difficult than accountable safety? Well, one of the things I mentioned is that it involves proving the absence of expected messages as opposed to the presence of unexpected messages. And the second thing I alluded to was this idea of Byzantine validators framing honest ones. Whatever process you give honest validators to be able to accuse Byzantine validators of causing a liveness violation, there's the risk that the Byzantine validators will instead use that to successfully accuse honest validators. So both of those intuitions we'll see appear fairly concretely in the argument I'll sketch on this slide. Right, and this is different from accountable safety. Accountable safety, the way you prove someone was Byzantine is you exhibit 2 signed votes that they cast for conflicting blocks. But assuming Byzantine validators can't forge signatures of honest validators, they're not in a position to frame honest validators in that way. So formally, our second impossibility result states that if you have a majority Byzantine validators, so at least half the validators are Byzantine, then in fact, accountable liveness is unachievable. It's unachievable even if you make the strongest possible timing assumptions. It's unachievable even for synchronous executions. So let's see the argument. Again, if you've seen some impossibility results for consensus protocols, whenever you see an impossibility result with like n/2 in the statement, you know the first step of the proof, which is imagine we split the player set into 2 groups of equal size, the players X, the players Y. We're going to look at one scenario where X are the honest ones and a different one where Y is the honest ones, and that'll put a consensus protocol in a bind, in a catch-22, where it's unclear who it can accuse. So for contradiction, suppose there were, in fact, a consensus protocol that guaranteed accountable liveness in synchronous executions with half the validators being Byzantine. And maybe, for example, the validators in X are all Byzantine. So the first step of the proof looks like the first step of some other arguments that we've already seen, which is that, the validators in Y cannot forge ahead. They cannot confirm any additional transactions without having heard at all from validators in X. The reason for this is the usual one, which is that we insist as a hard constraint on consistency in partial synchrony, including pre-GST. So if the validators of Y did in fact go ahead and start confirming transactions, even having not heard from half of the validators, well, then there's an execution where not just Y, but also X now being honest instead of Byzantine, and messages being now delayed between X and Y indefinitely, there's going to be an execution where X are also going to be confirming their own transactions, which in general will be conflicting with those confirmed by Y. And that's going to be a consistency violation, even with no Byzantine nodes in an execution, in a partially synchronous execution, which again is disallowed. Point being is that if if we're back in the world where the validators of X are Byzantine and they give Y the silent treatment, they never talk to them, it actually does force the validators of Y to stall. So given that the validators of Y stall in this execution where the validators of X are Byzantine and giving them the silent treatment, and note, this may well be a synchronous execution, so given that the validators of Y stall in this execution, by accountable liveness, they are now responsible for blaming some of the Byzantine validators. So by assumption of accountable liveness, it must be that Y somehow produces a certificate of guilt implicating the players of X. Given the messages that Y have received, and remember, they've received nothing from validators in X. So given the messages that validators in Y have received, which are just internal messages, they must somehow be able to blame successfully some Byzantine validator necessarily in X. But whatever procedure it was that the validators of Y, when they were honest, used to successfully accuse some Byzantine validator of X, that procedure can unfortunately be also used against them. This is the part where Byzantine validators are capable of framing honest validators. Specifically, imagine the roles are reversed, and imagine that actually the validators in X are honest, and it's the ones in Y that are Byzantine. But here's the thing, right? So the Byzantine validators, they can simulate what it was the validators in Y were doing when they were honest. Now Byzantine validators in Y can pretend that the validators in X are never talking to them, exchange whatever messages amongst them that they would have exchanged were they honest, and in fact X had all crashed, and then present that as the exact same certificate of guilt that the honest players had used in the previous execution. So that's going to be a certificate of guilt that will be accusing one of the honest validators, and that's a violation of accountable liveness. And one of the reasons this simulation is possible is exactly that old intuition we had, that one thing that may be tricky about liveness is that proving it requires proving the absence of expected messages rather than the presence of unexpected messages. So specifically in the prior execution, when X were the Byzantine ones and Y were the honest ones, right, because the Byzantine validators never sent any messages to the honest validators in Y, Y's transcripts had no messages signed by anybody in X. And yet despite that, despite there being kind of no presence of unexpected messages, only the absence of expected messages, despite that, we were assuming that Y somehow could come up with a certificate of guilt, even though they'd never seen a message signed by any validator from X. And so what that means is that when Y is actually Byzantine and simulating what the honest Y would be doing, they don't actually need to forge any signatures of the honest validators. They can't do that. That's what prevents this same proof from working for accountable safety. So because the honest validators have to just work with the only messages they know, which are only their internal messages, that's exactly why when Y is all Byzantine, they are perfectly capable of carrying out that simulation. So there's a lot of different ways you can go about trying to prove, guarantees for algorithms and protocols and so on. Like one typical way you might do it is you start from what you already know to be true and you try to prove something that's a little bit more general. One of the things I often tell my students, my PhD students, when I'm advising them on research, is to actually kind of go the opposite and think about what is the coolest statement, like the most general sort of, impressive thing possible that you don't yet know is false. So in other words, given all of the counterexamples, all of the impossibility results, all of the barriers that you've already identified, what's the most general, most interesting thing that circumvents all of them simultaneously, that you haven't yet falsified? So we can answer that question now about accountable liveness. And what we've seen is that, look, if you have half Byzantine validators, you're not going to get accountable liveness. Even in synchronous executions, it's just not going to happen because you have this framing problem. Furthermore, in partial synchrony, or more generally in half-synchrony, which again I'll define later, in half-synchrony, there's nothing you can do. As soon as an adversary is big enough to cause a liveness violation, they're also big enough to get away with it. You're not going to be able to actually identify any Byzantine validators. So, for accountable liveness, given what we know, what's the coolest thing that could be true? Well, we got to assume majority honest validators, so let's assume that. And then the hope would be that we might be able to guarantee accountable liveness for all, let's call it majority synchronous executions, where the network is synchronous a majority of the time before GST. And again, I'll give you a precise definition shortly. That is the coolest thing that could be true. That, in fact, is the main result of the paper. Okay, so we show how you can start from a protocol like Tendermint, add additional logic. I basically already told you what that additional logic is. And then you can define a blame function, which I'll get into. There's a lot to say there, so we'll get into that. You can define a blame function that guarantees accountable liveness. Okay? You need an honest majority validators, and you get accountable liveness in any majority synchronous execution. So to state this result formally, I need to tell you what I mean by majority synchrony. What do I mean when I say that the network is synchronous more than half the time pre-GST? So we're going to have a notion of a time step being either synchronous or asynchronous. And this designation is chosen by an adversary subject to constraints that we'll say on the rest of this slide. So the adversary gets to adaptively choose whether a time step is synchronous or asynchronous. Okay, so the protocol runs for a while, it's 1,000 time steps in, the adversary is like, given how things have gone so far, I'm going to declare this one to be asynchronous. Next time, I'm going to declare this one to be synchronous. Okay, so the adversary gets to declare this. And the timing assumption is that if a message gets sent by one validator, and sort of the execution continues, that message must be delivered at the latest after delta synchronous rounds time steps have passed. So if you like, you can think of every message as having attached to it a timer, which is counting down starting from delta. Every time the adversary declares a time step to be synchronous, the timer of every pending message counts down by 1. And the message has to be delivered once that timer hits 0. Of course, the adversary can also deliver messages early if it wants to. Now, for majority synchrony, let me just describe it in terms of concrete parameters. So we're going to have some window length, which is going to match up with the liveness parameter we're talking about. So again, I've been using 2 hours as an example. So we're going to split a 2-hour interval into chunks called views, which are meant to correspond to the views in a protocol like Tendermint. View, maybe let's call it 20 seconds. So if you have 2 hours, that's 120 minutes. If you have 20-second views, that's going to be 360 chunks of 20 seconds. So majority synchrony then refers to those 360 views and asserts that of the 360 20-second intervals, of the 360 views in the 2-hour interval, 181 of them should be synchronous, meaning that all of the time steps within that view are synchronous. So in general, majority synchrony says that within every sufficiently large time window, and again, that sufficiently large is going to be a parameter that you choose that sort of governs the strength of the timing assumption. Within every sufficiently large time window, a majority of the views within it are entirely synchronous. Okay, so that's majority synchrony. Obviously, it includes synchronous executions as a special case. It's just saying that you can actually have lots of asynchrony as long as you reasonably frequently have these sort of blocks, these views, where it's synchronous the entire time. As far as the parameter values, you should think of the length of a view as being O of delta, where delta is the maximum message delay under normal network operating conditions. So again, I'm thinking of like delta as maybe 2 seconds, and then the length of a view is maybe like 20 seconds. The window length is whatever you want. So it's just the window length is whatever window you're comfortable making a majority synchrony in. If you're comfortable making majority synchrony assumptions for 2-minute windows, well, then you can actually work with a liveness parameter of 2 minutes. If instead you're more comfortable having a window of 2 hours, that's where you think you probably have majority synchrony. That's going to correspond to dealing with liveness violations with respect to a sort of latency of 2 hours. So there's a few different ways you can interpret this definition of majority synchrony. One is just as a natural interpolation between two classical network models. On the one hand, the synchronous model, and on the other hand, the partially synchronous model. So here we're effectively parameterizing between those two according to the fraction of views pre-GST that are entirely synchronous. And one thing this work shows is that this extremely fine-grained parameterization between synchrony and partial synchrony is crucial for understanding exactly when accountable liveness is possible. Yes, it's true it's possible in synchrony and not possible in partial synchrony, but the full story is much more interesting. That what governs whether or not you can have accountable liveness guarantees is exactly whether you have majority synchrony pre-GST. We've seen there's this phase transition, impossible at half synchrony, possible at majority synchrony. A second interpretation of majority synchrony is, just as a way to formalize the promises that you're usually given by your internet service provider, right? They never promise you that your network's going to be super fast 100% of the time. They promise you sort of delays within some tolerance, at least some large portion of the time. And that concept maps fairly directly onto this fine-grained parameterization between synchrony and partial synchrony. So having now formally defined majority synchrony, I can state formally the main result, which is, indeed, you can augment standard protocols like Tendermint, Hotstuff, Streamlit, etc. You can augment those protocols along the ways we've already hinted at thus far, so that, first of all, you get all of the usual guarantees that these protocols offer, namely in partial synchrony, you have guaranteed consistency, you have eventual, meaning post-GST, liveness, provided less than a third of the validators are Byzantine, plus you still get non-trivial functionality, admittedly under extra timing assumptions, if the adversary is even larger than that. Specifically, as long as you have an honest majority of validators, but still, the adversary could be as large as 49% of the validator set, so it's certainly large enough to cause liveness violations. Up to 49% Byzantine validators, you can be accountably live, specifically in majority synchronous executions. So, in the rest of this talk, I want to provide you with a sketch of why this theorem is in fact true. Why it is that if more than half the validators are non-faulty, then in fact you can achieve accountable liveness in any majority synchrony execution. So we actually laid a fair amount of the groundwork for this result earlier on in the talk. You might remember, when we did our first impossibility result saying that, even for half synchronous executions, there's no hope of having non-trivial accountable liveness. Then we said, well, maybe you could get it if you made stronger timing assumptions about an execution. And then we spent some time building intuition for that idea. We said, well, let's look at the extreme case of synchronous executions and understand, what logic you might add to a consensus protocol so that you could, catch deviating Byzantine validators in that case. So let me now remind you of the key points of that discussion. So one of the things we did is we said, well, look, if there's a liveness violation in a protocol like Tendermint, it means you have a whole bunch of views where nothing happens. No blocks get finalized. So let's kind of zoom in on a view and ask what could have gone wrong? Why would you fail to finalize a block in a view? And we identified 3 different reasons why you might not finalize a block. Okay. So first of all, there might be network delays, right? So like maybe the block proposal never reached anybody on time, so nobody voted for it, so nothing happened. So back then we said, let's just think about the synchronous executions and like ignore this. All right. Now that we're dealing with majority synchrony, we're going to have to deal with this case. It'll be in a minority of views, but in a minority of views, the reason for failing to finalize a block might well just be network delays. A second reason is that the leader might be Byzantine and, for example, just not make a block proposal, in which case also nothing happens. Earlier in the talk, I said, let's not worry about that. I'm going to now again say, let's not worry about that. There's going to be a fairly simple hack to deal with this case that I'll show you toward the end of the talk. So just assume that leaders are honest. And then the only remaining explanation, right? So if in fact you're not having message delays and you have an honest leader, the only remaining possibility is that actually more than a third of the validators are Byzantine and they're deliberately blocking a block from getting finalized. For example, by not voting when they're supposed to be voting. And that non-participation by Byzantine validators is exactly what the blaming primitive was meant to accomplish. So remember, the additional logic that we're adding to a protocol like Tendermint is just that the validators will be broadcasting their progress through the gauntlet. The rounds, which had previously been delta time steps, we now make a little bit bigger, 2 delta, 3 delta, something like that. We make it a little bit bigger to make sure that all of the honest validators have time to keep each other in sync with the progress that they've made. So for example, if they're sort of casting a stage 2 vote because they've seen a stage 1 quorum certificate, they're going to go ahead and send that stage 1 quorum certificate to everybody else. If the view is synchronous, the other validators are going to get that promptly, and so they have no excuse for not themselves casting a stage 2 vote. And so that led to this idea of blaming. Okay, so we talk about one validator I blaming another validator J in some specific view V, if that validator does not hear from validator J the messages it's expecting to receive given the evidence that validator I sent to it. So for example, if it sent it a stage 1 QC and it does not subsequently hear promptly a stage 2 vote, then I will blame J in that view for possibly blocking progress. Now, one big additional complication compared to the synchronous executions we were talking about earlier is that, the reason I doesn't observe sort of expected progress from J might not be J's fault, it might be the network's fault if the current view happens to be asynchronous. So in asynchronous views, you will indeed generally have honest validators inaccurately blaming other honest validators because it was the network's fault, not the validator's fault. But the good news is that whenever the current view happens to be synchronous and you happen to have an honest leader, the only way you can fail to finalize a block is because of the deliberate non-participation of, call it at least like 34 out of 100 validators. And again, if the view is synchronous, the honest validators will observe this non-participation, and those 34 Byzantine validators will in fact be blamed by all of the honest validators. So to summarize that discussion, so again, we're not worrying right now about Byzantine leaders, assume all the leaders are honest, but we are worrying about the fact that a minority of the views of the protocol may be asynchronous. And as we said, in asynchronous views, all bets are off. Anybody might be blaming anybody. We really have no control over that because the network can do whatever it wants during those views. The good news is in synchronous views. And actually, there's 2 pieces of good news in a synchronous view. So first of all, honest nodes are never going to erroneously blame each other. If it's a synchronous view, everybody's messages are being sent promptly, so all the honest nodes observe the prompt progress of all the other honest nodes as well. So none of them are going to be incorrectly blamed. Of course, Byzantine validators might blame them. Okay, that's fine, but they're not going to blame each other. Furthermore, if this view fails to finalize a block, the only possible explanation is the non-participation of, again, call it 34 out of 100 validators, and that will be noticed by all of the at least 51 honest nodes. So you will have all of the honest nodes, 51 or more of them, blaming at minimum 34 Byzantine nodes as being responsible for blocking this view from finalizing a new block. And this is going to be basically all we have going for us in this result. We're going to take these two facts that in synchronous views, of which there's a majority, in synchronous views, honest validators never blame each other, and moreover, at least 34 Byzantine validators are blamed by all of the at least 51 honest nodes. Using that and nothing else, we're going to have to come up with a blame function which, based on the transcripts of the honest validators, identifies a Byzantine validator responsible for a liveness violation. That's the plan. That's what we got. That's what we got ahead of us. So suppose, a liveness violation occurs, right? So we have some liveness parameter. Again, I'm using 2 hours just for concreteness. And so suppose for 2 hours, some transaction has been pending and has not been confirmed. So that's a liveness violation. We need to invoke the blaming function as, by virtue of sort of claiming to satisfy accountable liveness, we're responsible now for identifying a Byzantine validator. So suppose a liveness violation occurs in some majority synchronous execution, right? So again, we have some liveness parameter, whatever. For concreteness, I'm using 2 hours. So suppose some transaction's been pending for 2 hours. If we're going to be accountably live, we better be able to identify with certainty some Byzantine validator. Okay, we need to define that blaming function. So let capital T be the number of views, okay, where this transaction's been pending. So in the example where we have 20-second views and 2 hours is the liveness parameter, this would be 360 views in a row where this transaction has gone unconfirmed. And we need to blame someone. We need to find some Byzantine validator who's responsible for this long delay. So where are we going to look for a Byzantine validator? Intuitively, we want to look for validators that get blamed a lot. So what does that mean? So we're going to have this notion of being majority blamed, and that means, say there's 100 validators for concreteness. Majority blamed in a given view means that 51 validators blamed you. Okay? That means you were majority blamed in a view. Now, suppose you have a validator that's actually majority blamed, so 51 out of 100, blame it, in a majority of the views. So if we're talking about 360 views in a row with no progress, we mean 181 of those 360 views, 51 of the 100 validators blame you. So that's getting blamed a lot. And in fact, if you're blamed that much, there is no way you're an honest validator. It cannot happen. Okay? Why not? Because remember, it's right here on the slide, in any synchronous view of which there's 181, you will not be blamed by any honest validator of which there's 51, counting yourself. Okay? So in every synchronous view, 181 of them, you're blamed by at most 49 people. So you are not majority blamed in 181 views. So if you find a validator that's blamed by more than half the validators in more than half the views, you can confidently declare that validator to be Byzantine. And you're done. That's someone to blame. The issue, unfortunately, is that such a validator may not exist. Now, life would be rosy if we had a relatively small attacker. If there were only 34 Byzantine validators out of the 100, then we'd be in great shape. The reason being is that in those 181 synchronous views, the only way you would fail to finalize a block is if all 34 of the Byzantine validators sort of withheld participation. And they would then all get caught by all of the honest validators. So all 34 Byzantine validators would get majority blamed in every synchronous view, at least 181 of them. So every single one of them would be identified as a validator that's majority blamed in a majority of the views. The tricky part is we're being more ambitious and we're allowing the adversary to have as many as 49 validators, 49 Byzantine validators. And in any given synchronous view, we're only guaranteed to blame 34 out of those 49. And so if the Byzantine validators that we blame sort of rotate within the 49 Byzantine validators across the synchronous views, then in general, we're not going to be majority blaming any of the Byzantine validators with 181 or more views. That's kind of the issue. But it turns out we can actually fix this argument. We just need one extra step. So the idea is we're going to take the 360 views we're dealing with, and then we're going to filter them. Okay, we're going to look at a subset of those views, less than 360, and we're going to filter them in such a way that we only throw out asynchronous views. All the synchronous views sort of pass through the filter. Then we're going to use the exact same heuristic as before. We're just going to look for validators that are majority blamed in a majority of this filtered set of views. And then we're going to actually show that there has to be such a validator, and that validator has to be Byzantine. So what exactly is this filter? I'm sure you're wondering. Given these 360 views, how do I sort of strip out some asynchronous ones? And how can I be so sure that what I'm throwing out is asynchronous? And at a high level, the idea is we're going to have a similarity measure between views in terms of which sets of nodes get majority blamed in those views. And what we're going to see is that for the similarity measure, each pair of synchronous views looks very similar to each other. And then what we're going to do is we're going to throw out views that do not look similar to the synchronous views. Those are going to be the asynchronous views that we're throwing out. So let me make this precise using a graph. Graph in the sense of like a network. Vertices and edges. It's going to be an undirected graph. Vertices of this graph will correspond to the views that we're talking about. So if there's 360 views, this is going to be a graph with 360 vertices. Intuitively, we're going to put an edge between a pair of vertices if the corresponding views are similar in terms of who is majority blamed in those views. So in more detail, by A sub v, v here is a view, by A sub v, that denotes the validators that are majority blamed in view v. Okay, so if you're in A sub v, that means 51 out of 100 validators blamed you in view v. Okay, so those are the validators in A sub v. We're then going to put an edge between two vertices in the graph, right? So two views, v and w, if and only if the majority blamed nodes overlap a lot between those two views. So there should be more than n over 6 nodes. So for example, like 17 nodes out of 100, more than n over 6 nodes that are majority blamed in both view v and in view w. If that's the case, we put the edge in the graph. If it's not the case, we don't put the edge in the graph. The first thing to notice is that the synchronous views are going to form a clique in this graph. If you have two synchronous views, v and w, there will be an edge between v and w. So why is that true? Well, remember, one of the two really good things about synchronous views is that we're guaranteed that at least n over 3 Byzantine validators, so like 34 out of 100, at least n over 3 Byzantine validators are going to get blamed by all of the honest nodes, of which there's at least 51 out of 100. So in any synchronous view, 34 Byzantine validators at least get majority blamed. Now, we're also assuming there's at most 49 Byzantine validators. So you may miss some, but you're going to miss at most 15 in any given synchronous view. So if you have two different synchronous views, v and w, both of which majority blame at least 34 out of the 49 Byzantine validators, well then in the overlap, there will be at least 17, actually a little bit more than that, at least 17 Byzantine validators that are majority blamed in both v and w. So again, the synchronous views are going to form a clique in this graph. In that sense, every synchronous view sort of resembles every other synchronous view. So I can now define for you the filter. So we start from these 360 views, and we're going to extract from it a subset. I'm going to call that subset capital X. And we're going to make sure that all of the synchronous views are part of that subset capital X. So to qualify for membership in X, you need to pass two tests. Both of these tests basically kind of say like you look as if you're a synchronous view in the following sense. So first of all, to qualify for membership in capital X, as a view, it better be the case that 34 or more validators get majority blamed in your view. That's definitely true for any synchronous view. Specifically, 34 Byzantine validators get majority blamed in any synchronous view. And in general, for qualify for membership in X, there better be 34 or more validators that get majority blamed. Second of all, it should be the case that you have high degree in this graph capital G. In other words, there should be a lot of other views that look a lot like you in terms of which validators are getting majority blamed. So specifically, again, if we think of the graph as having 360 vertices, to qualify for membership in capital X, you need to have degree at least 180 in that graph. So there need to be 180 other views where you have healthy overlap between who gets majority blamed in you and who gets majority blamed in the other view. And as we said, this will hold for any synchronous view. The 181 synchronous views form a clique on 181 vertices in that graph. So all of those vertices will have degree at least 180, if nothing else, with the other 180 synchronous views. I'm happy to report that after this filtering step, the simple idea we had earlier of returning a node that's majority blamed in a majority of the views, that idea now provably works. So concretely, the proposal for the blaming function is return an arbitrary validator that's majority blamed in a majority of the views of X. So X maybe it has only 240 views. So the proposal is find a validator that's blamed by at least 51 out of 100 validators and at least 121 out of the 240 views of X. The old reasons why we can't possibly be blaming an honest validator are now only more true. Right? Remember, one of the good things about synchronous views is no honest validator blames any other honest validator. So no honest validator is blamed in any synchronous view. All of the synchronous views were a majority even in the original 360. They've all made it into X, so there's certainly a majority within X. So for example, maybe 181 out of the 240 views of X are synchronous. Honest validators cannot be majority blamed in any of them, so they're definitely not going to be named by this particular blaming function. The piece that was missing before, and which now happily has fallen into place, is that there is in fact guaranteed to be such a validator. And that validator, of course, must necessarily be Byzantine. So that's a validator you can hand back as the output of the blaming function. So the final thing I want to do is actually prove this key lemma for you. It does fit on a slide. It's basically an averaging argument. And so again, what are we showing? If there's a liveness violation, so if you have 360 views in a row with no progress, then in fact there must be some validator that gets blamed a lot. Specifically, it gets majority blamed, like 51 out of 100 validators, in a majority of the views of X, like 121 out of 240 views of X. As we've seen, that cannot be an honest validator. That must be a Byzantine validator if it exists. So let's show that it exists. So let me organize the averaging argument using a 0-1 matrix capital M. Now keep in mind, capital M is only for the analysis, right? So that's not in the blaming function per se. It's not in the consensus protocol. It's just in the analysis of the correctness of this blaming function. All right, so that said, in our minds, we form the 0-1 matrix capital M, the rows of which are going to correspond to the Byzantine validators. So maybe there's 49 of them out of the 100 original set of validators, for example. And the columns are going to correspond to views that pass the filter, views of capital X. So maybe we have 240 columns left over from the original 360. And this matrix is just going to be an indicator matrix for which Byzantine validators get majority blamed in which views. Okay, so a given matrix entry is going to be 1 if and only if the Byzantine validator corresponding to that row gets majority blamed in the view corresponding to that column. Okay, so indicator matrix for which Byzantine validators get majority blamed in which views. So the plan now is going to be to argue a lower bound on the average column sum, which then, looking at things the other way, will give us a lower bound on the average row sum, and that'll imply the existence of a row with lots of ones. That is, it'll imply the existence of a Byzantine validator majority blamed in lots of views, a majority of the views of X. So to get a handle on the column sums, let's start with the easy case of a column that corresponds to a synchronous view. So one of the good things about a synchronous view is that 34, say, out of 100, at least n over 3 Byzantine validators are going to get blamed by all of the honest validators, so by a strict majority of the validators. So what that means is that any column of M that corresponds to a synchronous view will have at least n over 3 ones in it. Okay, so we've lower bounded the column sum of the synchronous columns by n over 3. So what about the columns that correspond to asynchronous views? And this is where it seems like there should be nothing we can say. Remember, asynchronous views, like anything can happen, anyone can blame anybody because messages are not being delivered. So this is sort of the key step. This is the reason why we define the filter the way that we did. We're going to now use the fact that the only asynchronous views that make it into X, so that could be a column of this matrix, in fact have to resemble a synchronous view. Okay? And therefore also have, maybe not quite as big a column sum, but they have a column sum a lot bigger than 0, at least as it turns out n over 6. So let's talk through why that's true. All right. So suppose you're an asynchronous view and you didn't get filtered. You made it into capital X. So what does that mean? So that means in that graph, capital G, like the graph with 360 nodes, you had to have degree, this asynchronous view had to have degree 180. And so in particular, because there's only 179 asynchronous views and there's 181 synchronous ones, one of its neighbors in that graph must have been a synchronous view. That is the sense in which any asynchronous view in capital X resembles a synchronous view. It is a neighbor in capital G of some synchronous view. So what does that mean? Well, what does it mean for two vertices, two views, to be neighbors in that graph capital G? It means there's a lot of validators in common that get majority blamed in both of those two views. So what does that mean? Well, we have this synchronous view, right, where no honest validators get majority blamed, and at least n over 3 Byzantine validators get majority blamed. And then we have this asynchronous view, but it has to blame largely the same validators, okay, at least n over 6 of the same validators as the synchronous view. The synchronous view only blames Byzantine validators. That's the only opportunity for overlap. So this asynchronous view has no choice but to itself blame not necessarily all of them, but by definition of being an edge in the graph G, it has to blame at least n over 6 of the Byzantine validators that are blamed in that synchronous view. So what that means is that in this column corresponding to an asynchronous view, by virtue of blaming many of the same validators as the synchronous view that it neighbors, it itself has to have a large column sum, namely at least n over 6. So what does that imply about the average column sum of this matrix capital M? Well, we have synchronous views that are at least n over 3. We have asynchronous views that are at least n over 6. Originally, in our original 360 views, a majority were synchronous. We've now thrown out asynchronous views and kept all the synchronous views. So in what's left, in the 240 views left, capital X, we still have 181 synchronous views, so they're definitely a majority in capital X. So that means the average column sum is going to be at least the average of n over 3 and n over 6, which is n over 4. So in total, we have n over 4 times the number of columns times the size of x ones in this matrix capital M. All right, so that was the first part of the argument, the important part of the argument where we lower bound the average column sum. Now we just look at the matrix from the row perspective instead of the column perspective. Remember, at most half the validators are Byzantine. There's less than n over 2 Byzantine validators. That's the number of rows. So if you have n times the cardinality of x over 4 ones spread over at most n over 2 rows, that means the average row sum has to be at least the cardinality of x, the number of columns, divided by 2. There has to be some row with some at least the average. There has to be some row with some at least the number of views in x over 2. And that, what does that mean? That row is a Byzantine validator, and it has a 1 in over half the columns. That means it's majority blamed in a majority of the views of x. And so that's what we wanted to prove. The fact that there must be a row that has 1s in over half the columns, that exactly means there must be a Byzantine validator for us to blame. There must be a Byzantine validator that is sort of revealed as such by virtue of being majority blamed in a majority of the views of x. And that's it for the key lemma, and therefore for the proof of correctness of this blaming function. All right, so you may not remember this, but there's actually one more detail that I really owe you. So when we talked about, a liveness violation, that means a bunch of views in Tendermint fail to finalize blocks, and we said, what are the reasons why that could happen? And there's really 3 different reasons, and we've only been dealing with 2 of them. Okay? It can happen because of asynchrony. If you're in a majority synchrony execution, that only happens in a minority of views, but still it can happen, and we've had to deal with it, and we just did. It can happen because of non-participation by a large adversary, so by 34% of the validators, if they don't participate, that can actually block finalizing a block. But then there's this third one that you might have a Byzantine leader, right? And the Byzantine leader, for example, could just not make a block proposal, and that's yet a third reason why a view of Tendermint might fail to finalize a block. And thus far, we've just been ignoring that. We've just been saying, suppose every view has an honest leader, and the only possible explanations are either asynchrony or non-participation by a large adversary. So now let's actually talk about the hack, frankly, which allows you to actually kind of assume away the problem of Byzantine leaders. So the idea is quite simple. Let's suppose we implement Tendermint so that independently each view, it randomly samples a uniformly random validator to be the leader of that view. So we're assuming that more than half of the validators are honest. So that means you have a 50% chance or better of getting an honest leader in any given view. So it's kind of like a coin flip. Heads, you get an honest leader. Tails, you get a Byzantine leader. So rather than doing the analysis at the granularity of views, we're going to do it at the granularity of what we're going to call superviews, which is just a sequence of k consecutive views, where k is a parameter we can set however we want. And so notice that over k views in a row, you're very likely to get at least one honest leader. Okay, all but with probability 1 over 2 to the k. And the blame game is then carried out, again, at the granularity of superviews rather than of views. So if you're a validator I, and in some view, V, within some superview S, you observe some validator J not making expected progress. So like not casting a stage 2 vote, even though you yourself sent them a stage 1 quorum certificate. Well, then you think to yourself, you know what? Well, if this was a synchronous superview, the only possible explanation for that fact would be that they are Byzantine, because they're just deviating from the protocol, from what they're supposed to be doing. And so you, validator I, would then blame that validator J at the level of this superview S. Okay? So the blame game is carried out on superviews, not on individual views, and you blame someone if you don't like what you see in any of the views within a superview. And the previous analysis, which assumed honest leaders, basically carries over to superviews without assuming honest leaders. Right, because if you have a liveness violation, that means there must have been a bunch of superviews in a row where Tendermint failed to finalize any blocks. So why might that have happened in one of these superviews? Well, one reason is you might have had asynchrony, okay, which again could happen, but we're going to assume happens in a minority of the superviews. A second reason would be a Byzantine leader, okay, a Byzantine leader in every single one of the views in the superview, but that happens with probability only 1 over 2 to the k and can kind of be absorbed into other parameters of the analysis. And then the only remaining option, okay, if you're synchronous for the superview, and in fact you get at least one honest leader, is that it must be due to non-participation by Byzantine validators, and this will be observed, they will be blamed, and all of the previous blaming analysis then carries over. So that wraps up the analysis. So let me just sort of remind you what are the main contributions of this work. So first of all, we provide for the first time a definition of accountable liveness. I think the definition is, for the most part, what one would have expected. There's a couple of tweaks that you need, but it very closely parallels the very successful definition of accountable safety. But we saw that you need to make some compromises to achieve accountable liveness that you did not have to make to achieve accountable safety. So for example, even if you only want accountable liveness in synchronous executions, again, as always, subject to the hard constraint of being consistent and eventually live in partially synchronous executions, even if you only want accountable liveness in synchronous executions, you cannot do it unless you have an honest majority of validators. And again, this is different than accountable safety, where you do not require any cap on the number of Byzantine validators to guarantee accountable safety. And we saw in the proof the fairly interesting reasons for this difference, which is about to what extent Byzantine validators can frame honest validators, basically kind of fabricate what looks like misbehavior by the honest validators. For consistency violations, they simply can't do that. So generally, certificates of guilt for consistency violations involve sort of signed votes for conflicting blocks, and Byzantine validators can't forge signatures by honest validators. So they're in no position to frame them and make up some fake certificate of guilt for them. That's why you get accountable safety with no cap on the number of Byzantine validators. Whereas liveness, you're sort of dealing with the absence of expected messages rather than the presence of unexpected messages. So what that means is you have to come up with certificates of guilt even if you literally have nothing from the Byzantine validators to work with, even if you don't have any, say, signed messages that you've ever received from them. But that means the Byzantine validators, if there's enough of them, can then turn this procedure on its head and actually fabricate sort of fake evidence of misbehavior by the honest validators. And that's the reason for this n over 2 threshold. The second compromise that we saw that we need to make is that you cannot just have this for free in partial synchrony. You're going to need to make additional timing assumptions, And in fact, even if you make a half-synchrony assumption, so pre-GST, the communication network is synchronous half the time, that's not good enough. As soon as an attacker is large enough to cause a liveness violation, as soon as it has at least a third of the validators, it is already large enough to elude any kind of punishment, to elude any kind of identification. The good news is, given 2 and 3, the coolest thing that could be true is in fact true, which is you can modify Tendermint or any number of other standard protocols so that they remain consistent and eventually live in partial synchrony. And on top of that, if you have an honest majority of validators, you can get accountable liveness in any majority synchronous execution. Any execution where the network is synchronous for a majority of the views leading up to GST. Now, I don't know if you remember, but back at the beginning of the talk, I actually mentioned a third cool fact about accountable safety, which is that following a consistency violation, not only can you identify some Byzantine validators, you can actually identify a lot of them. You're guaranteed to identify at least n/3 Byzantine validators. That may not be all of them, but if you think about it, that's the best you can hope for, the minimum number that's sufficient to carry out a consistency violation. So in this talk, we haven't really had time to discuss how many Byzantine validators are going to be successfully identified following a liveness violation. In the analysis I just showed you, we contented ourselves to at least identify 1. If you look at the paper, you'll see that actually a good chunk of the paper is exactly about this question, exactly about how many Byzantine validators can you hope to identify following a liveness violation. And again, the answer is just more complex than it is for accountable safety. There are cases where you will do as well. So for example, if there's only n/3, like 34 out of 100 Byzantine validators, so the attacker is just barely big enough that they can cause a liveness violation, then if they do cause a liveness violation, you'll catch them all. So that's great. You'll get your n/3 if the adversary size is only n/3. Similarly, if it's a synchronous execution, you'll get your n/3. But if the adversary is bigger than n/3, and or if you have some asynchronous views, you will actually provably need to identify less than the holy grail of n/3 validators. And again, if you want to understand exactly how the number you identify depends on the strength of your timing assumptions and depends on the size of the adversary, check out the paper for that. So that's the story so far for accountable liveness. Definitely, I would love it if this was just sort of chapter 1 of many more chapters to come. I would love to see researchers in the community sort of take these ideas and run with them. But that's what we've got for now. So thanks very much for listening, and I'll see you next time.